Thank you very much, and yeah, thank you for inviting me to this wonderful conference. Yeah, today's topic of mine is the faithfulness of the representation of B3 modulo P. Yeah. My talk is divided to 4 sections. In the first sections, I will briefly review some basic preliminaries of the representation. I guess most of people here are well known about this topic, but yeah, so I'll take a crash course, just crash course. Yeah, the Artin braid group on 3 strands B3 is the group having presentation as follows. In which there are 2 generators and 1 relation. And this group has a faithful representation in GL2Z inverse, where the entry, each entry is a wrong polynomial, and yeah, the split matrices are given like this. For higher n or just n equal 2 cases, we may define the representation of Bn, but in this talk, we just focus on the B3 cases. But there's just one remark on the faithfulness of the representation. The representation of Bn is known to be faithful when n equals 2 or 3, and non-faithful when n is not smaller than 5. Yeah, the only non-solved case is the case n equals 4. But yeah, there are some partial results, at least when we taking modulo P. Cooper and Long shows that the Burau before modulo 2 is non-faithful, and modulo 3 and 5 is also non-faithful. Notably, some algorithmic methods plays a significant role in finding counterexamples for the level 2 cases. Cooper and Long used the gap to gap, and Gibson, Williamson, and Jacobi use more delicate algorithm. But yeah, my goal in this talk is quite simpler and humbler. The topic of my talk is just about the Burau of B3 modulo P. This question is open when P is larger than 2. In this talk, we provide an algorithm to determine whether phi P is faithful, given a prime P such that P equivalent to 2 or 5 modulo 6. It is generalizable to any P, and I posted an archive preprint, but yeah, the general cases are too technical, and yeah, I've no time to cover all of them. So yeah, I just briefly review the faithfulness proof for original phi. Yeah. The center of the proof is generated by 1 element, and the quotient of B3 by center is isomorphic to the modulo group PSL2Z. One may show this fact by taking a proper representation of PSL2Z and just by using the teacher transformation. Now, so we have a sequence, so exact sequence as follows. Yeah, this is very basic fact of the representation, but this is very first building block of my work in this talk. Yeah, on the other hand, consider the projective evaluation at T2 minus 1 of phi B3 to PSL2Z. Yeah, generated by two matrices, 1, 1, 0, 1 and 1, 0, minus 1, 1. One easily see that the image generates the whole modulo of PSL2Z. Yeah, it is not so hard. Yeah, it's quite elementary. And the corner of the evaluation is generated by just delta square. So the phi lemma established the basicness of phi. Yeah. Also, yeah, everything is simple, but however, the classical proof we just reviewed is not directly applicable to the cases take modulo P. Yeah. In this case, we have almost the following. Mean the evaluated image of phi P generates a whole finite group SL2FP. This follows from the strong approximation and the whole generation of PSL2Z. But unlike before, the kernel itself has no use now. So we need another tool to understand the group structure of phi P V3 aside from evaluation. So from now on, we focus on unitarity, crucial property of the representation. At first, let us just define matrices M and J, and define Si to be the projective image of M phi sigma I M inverse. I mean the conjugation of the Burau image of the generators. Then we have two matrices as follows. So as usual, by defining the involution x to x bar to be the anti-rise map taking T to T inverse. Then element x in the group generated by S1 and S2 satisfies the unitarity as follows. Yeah, it is quite it's just looks like usual Hermitian unitarity, but unlike that of the original Burau representation, because we use matrix in between Z, which is diagonal. So we start diagonalized of the Hermitian form, but this requires a kind of trickiness because the matrix S1 has a non-trivial denominator 1 plus T, so it doesn't seem like a good form to handle in this now. But the issue about the denominator is able to be relieved by taking some finite index subgroup, observe that any form of matrix ABCD and take the conjugate by M, then by direct computation, we have lemma 2, where the conjugated image of matrix ABCD by M has Roland polynomial entries, if and only if kind of the original 1, 2 entry is 0 modulo P when evaluated T to -1. So in this situation, we may define the upper Hecke congruence subgroup. This is a quite well-known group, well-known congruence subgroup of PSL2Z. Combining lemma and lemma 2, we restate the lemma 2 by using the Hecke congruence subgroup. And on the other hand, consider the natural projection pi p from just GL to PGL, where the corner is the diagonal subgroup with the same diagonal entries. For example, T0, 0, T, or minus T, 0, 0, minus T. For this map, the kernel generator delta square satisfies the following identity. And by computing some elementary, in fact, it's not so elementary, but which at least we may guess the lemma 4, and we skip the full-fledged proof, but we may guess that the intersection of the kernel and the modulo P image of the Burau representation is generated by just phi p delta square, because just it has the conjugated image which is diagonal like above. And combining things before, we may define our map mu p from PSL2Z to phi p bar. Bar means the image is projective linear group by like this. From the facts I stated, we have the following commutative diagram as follows. In the upper row, the middle 5b3 is the usual Burau image, and the upper row is induced by just evaluation of T at -1. And the central arrow, down arrow, is used by modulo P map, just usual modulo P map, entry-wise, and the lower sequence is induced by natural projection pi P, I stated. Then mu P is the map from PSL2Z to 5P bar B3, making the diagram commutative. Yeah, this is just a result by just yeah. One may prove this by just identifying the kernels. This lemma 4 provides us with a neat interpretation of the phase points problem. So the middle down arrow 5P, middle down arrow mod P is injective if and only if mu P is injective. So since the original phi is faithful, we have corollary 1. Moreover, since the congruent subgroup gamma 0 P has index P plus 1 in PSL2Z, considering the cosets, we have this is just from direct computation. We have corollary 2 stating that the phase points problem depends on the phase points of mu P restricted on gamma 0 P. And fortunately, there is a classical theorem of Rademacher on the structure of gamma 0 P. So yeah, I guess I should skip the details, but the goal is we may use the usual generators S and T of the modulo group, and we may write down some words VK in S and T. Then we may explicitly find the finite generating set of the Hecke congruent subgroup. Moreover, there is we may calculate the exact minimal rank of the group. So in these cases, we may see that the Hecke congruent subgroup gamma 0 P is a pre-product of some cyclic groups whose some infinite cyclic groups and possibly 2 cyclic groups of order 2. So this is another tricky part, but the point is we may choose a finite index subgroup of PSL2Z. By using this, we may define KP, which is index 2 subgroup of gamma 0 P, and we may show that KP is free, and we may explicitly calculate the rank for every case by some TensorPool, we may define, we may depend on the Reidemeister-Schreier process. Yeah, so by using the KP, subgroup KP, the problem is more reduced to the case that domain is KP, and in this case, we have placed it a free group in the domain of mu p. And in this case, we may have we may hopefully use algorithms about free groups. On the other hand, we now consider the target group. The target, by corollary 2, it suffices to analyze the unitary group in the PGL2 and PTT inverse. I mean, the entries are all Laurent polynomials. It satisfies the unitarity. It's natural to extend the unitary group as follows. In fact, we will use the project simulated group, the extended unitarity. This group has a crucial subgroup. I call it the quaternionic subgroup QF. QP, to be the subgroup having some explicit form of entries. Then the index of QP in SP is 2 or 4. Sorry, I guess I am going too fast, but sorry. So because I have not much times, I guess I should jump to the conclusion. So the point is the quaternionic group is freely generated by some elementary generators. I mean, explicit form. They have explicit forms, and we may calculate the free length, which is exactly p. And from the construction of KP, the image of the restricted map mu p on KP is contained in the quaternionic group QP. So corollary 3 established that KP is finitely generated free. Thus, we have reached a situation where we have to decide whether or not a map between finitely generated free groups is injective. In this case, there is a neat algorithm that is Stalin's folding. In this algorithm, we can always compute the rank of the image. So we may construct an algorithm to decide whether phi p is faithful. First, finding a generating set of KP. Second, computing the image under mu p. Finally, computing the length of the image in QP by Stalin's folding. Since finitely generated free groups are Hoppian, the injectivity is equivalent to the fullness of the rank of the image. For example, there are only I have two cases, p equals 2 or 5. In case P equals 2, by the structure theorem, Q2 is rank 2 for a group generated by 2 elementary generators. And we may compute following Rademacher. K2 is Fourier generated by S square and SV1, which are mapped to G20 and G21 inverse G20 respectively. And we directly see that these elements freely generate the entire free group Q2. So the free rank of mu2K2 is 2, which implies phi 2 is faithful, which recovers the result of Couperon. And this is new results. In case P equals 5, situation is more complicated. In this case, K5 is freely generated by 3 elements, which are mapped to following elements, respectively under mu5. Using some method in free group Q5, for example, times fooling or just computation by hand, you may easily see that the free rank of mu5 K5 is 3, and it is full since it is equal to the rank of K5. Therefore, we have the 5 is also faithful. We conjecture that phi p for every p is faithful, but when p is large, then the computation is very tricky and takes a very long time. So I checked the cases from P to P equals 2 to 13, but on the higher P, I am not sure the computation is done by a good or more faster method. So yeah. Thank you for listening to my talk.
Thank you. Okay, so are there any questions for Donsung? Oh, I just noticed, Donsung, your camera has been frozen.
Oh.
So if you restart it, it should be fine. But
sorry.
No, it should be all. Okay, now
yes.
now you're moving again.
Yeah.
Are there any questions for Donsung?
Am I? Do you hear me? I don't hear myself.
Yeah.
So, Ignat Soroka, my name is. Thank you for a nice topic and nice talk. I was wondering if one wants to extend your results to rank 4, like dimension 4 of braid Burau representation. What will be the main obstacle? What ingredient we miss?
The dimension. The first trend case is very tricky. Mainly, I guess the main obstacle is the target group, structure of the target group. I mean, my method depends on the full characterization of the unitary group of the star diagonalized form of the unitarity of the Burau refutation. But when we extend to the dimension 4 cases, the unitary, I am not sure we can even the yeah, you can even compute the whole structure of the unitary group in the
I
target.
see. Okay, thank you.
Thank you.
Are there any other questions? Well, if not, let's thank Donsung again. Well done.